Continuing with projectile motion problems, Holiday and Resnick, chapter 4. We have this figure here on the side here. A ball is thrown up onto a roof, landing 4 seconds later, a height of 20 meters above the release level. The ball path just before landing is angled at 60 degrees with the roof. Find the horizontal distance d it travels. See the hint, problem 39. What are the magnitude and see the angle relative to the horizon of the ball's initial velocity. Here I've drawn a sketch and I've just reversed the motion. And we have given to us that this angle here is 60 degrees. Also, we know that this is 20 meters high and that it takes 4 seconds to reach where it's going to hit the ground. 4 seconds for D. So we'll start off with this formula. V equals V sub O T sine theta minus 1/2 GT squared plus Y sub O. Now Y sub O is going to be, this is going to be our 0 point, and Y sub O is going to be this 20 meters. So we'll set V, this is Y. We'll set Y equals 0 to solve this problem. So we're going to have 0 equals V sub O T sine theta minus 1/2 GT squared plus 20 meters. And we want to solve for V sub O. So we'll just take the rest of this on the other side of the equation. It's V sub O T sine theta is going to equal plus 1/2 GT squared minus 20 meters. We're interested in V sub O, so we can divide this T out. T would make this just T when we divide by T. And we have 20 over T. This goes to V sub O equals, we put this, all this here. We know 1/2 of G is 4.9. 4.9 T minus 20. And what do we have left? Sine theta times T. So this is the V sub O we're trying to calculate. So let's just put some numbers to this. This is V sub O, which we don't know, times 4 seconds times the sine of 60 degrees minus 1/2 of G is 4.9 times T squared, T is 4, which is 16, plus the 20, which is the height. So we're going to have V sub O, 4 secs times sine of 60 degrees is going to equal 4.9 times 16 comes out to be 78.4. And this is a minus 20. So we're going to pause and I'm going to solve this. When we solve for V sub O, we're going to get 16.87 meters per second. That goes right up here. Now, what this allows me to do, we know that the velocity in this direction, the x direction, is constant. So we're going to be able to figure out the distance between the building and where this projectile touched down. So let's do this. We know that x is equal to V sub O cosine theta times t. So this distance here is going to be x equals V sub O cosine 60 degrees times 4 seconds. We'll run that real quick on the calculator. V sub O is 16.9 times cosine 60 degrees times 4 gives me 33.8 meters. So it's 33.8 meters between the building and where it touched down. So we need the Vy component. And what we know is that y is going to equal y sub O plus V sub O sine theta times t minus 1/2 gt squared. So let's take the derivative of that. We have dy dt. That's a constant, so it goes to 0. That with respect to t is just going to give us V sub O sine theta. The derivative of this, 2 times 1/2, is going to give us just 1. So we'll have gt. I just want to show you that so you'll see where they're getting this formula from for velocity on the side. They're just doing the derivative of the position vector. Now we know that this Vy component, V sub O is 16.9 times the sine of theta, which is theta is 60 degrees, that's 0.866, minus 9.8 meters per second times 4. We're going to pause and do the calculation on this. So when we do this calculation, we get a minus 24.5 meters per second. So to get the magnitude of this V when it hits the ground, just before it hits the ground, I'm going to do a square root for V. The magnitude is going to equal square root of Vx squared plus Vy squared. Now, I know Vy, we just calculated that, but we can get Vx from right here. So if we did a derivative on this, we'd have dx, dt, that turns that in terms of velocity, V sub O, cosine of 60 degrees, and from previous calculation, I know that is 8.45 meters per second. So let's just put this all together now. We got V, the magnitude of V is equal to the square root of 8.45 squared plus 24.5 squared, and that will equal 25.91, which is, we'll just say 26 meters per second. So that's this vector here. Now, what the problem wants is when it was in this situation, it wants this vector and this vector. So what we're going to do is just flip these up. We're going to flip this up this way and flip that one that way, and that will represent the what the problem was asking for. So we'll flip this vector up. And that vector there is 24.5. meters per second. And the we'll have the x component of the velocity, which is 8.43 meters per second. Should be much shorter. Let's shorten it up some. And then we'll have this component, which we computed as 24.5 meters per second. That's answering. Now we need this theta right here to complete this problem. So theta, we're just going to do our thing, is equal to 10 to the minus 1 of 24.5 over 8.43, and that's going to equal 71.01 degrees. So that answers. So the original velocity when they fired it up, when he threw the ball up this way, 24.5 meters per second. At an angle of 71.01 degrees.